Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. In episode 91 of the Network Plus Prepcast, we turn our attention to load balancers, critical devices in the realm of modern network design. Their primary function is to distribute traffic across multiple servers, ensuring no single device becomes overwhelmed. This traffic distribution allows for better performance, reduced downtime, and improved responsiveness. As networks grow and demand on services increases, load balancers play a vital role in sustaining operations. For the certification exam, knowing how load balancers operate and where they fit within network topologies is essential to understanding scalable and resilient infrastructure. Load balancers are more than just traffic directors. They are foundational components that allow networks to grow while maintaining performance. By spreading connections across multiple back-end servers, they create room for expansion and support high availability. They also contribute to redundancy by redirecting traffic away from failed or overloaded nodes. This design improves fault tolerance and guarantees that services remain accessible even during high usage periods or component failures. On the exam, you may be asked to evaluate load balancer roles in maintaining continuous service and supporting distributed application environments. The most basic function of a load balancer is to direct incoming network requests to one of several back-end servers. This distribution helps prevent any single server from becoming a bottleneck. Load balancers monitor sessions and can manage client connections based on current server load, request type, or session history. They respond to client requests quickly and aim to minimize delay while keeping response times consistent. Load balancers may also prioritize certain requests or redirect users based on defined criteria, depending on the configuration and operational layer. In a typical network, load balancers are positioned between clients and the back-end servers that deliver applications or services. They may reside at the edge of the network, intercepting external requests before they reach the internal systems, or they may be placed internally in front of an application cluster. Their placement is strategic. They must be able to view and analyze inbound traffic while deciding how best to route it. This central position allows them to control the flow of traffic and act as a protective layer between users and back-end infrastructure. There are several different types of load balancing, each with its own operational characteristics. Layer 4 load balancing is based on transport layer information like source and destination IP addresses and ports. It uses minimal processing and can distribute traffic efficiently across servers. Layer 7 load balancing, however, is application-aware and can make decisions based on data like uniform resource locators, cookies, or application headers. Additionally, load balancers may be implemented in hardware for high-speed processing or in software for flexibility and easier integration into cloud environments. One of the simplest and most common distribution methods is round-robin. In this method, the load balancer sends each new request to the next server in a predefined sequence. This creates an equal rotation across the available servers and works well when requests are similar in nature. Round-robin load balancing is stateless. It does not keep track of session history, so it assumes all servers are equally capable. While efficient for many scenarios, it is less effective when certain servers become overwhelmed or when sessions need to be persistent for user continuity. For more advanced environments, the least connections method offers greater efficiency. This approach directs traffic to the server with the fewest active connections. It continuously monitors the number of open sessions on each server and updates its routing decisions dynamically. This method ensures that heavily loaded servers receive fewer new requests, allowing the system to balance itself based on current usage. This technique is especially useful for applications with long-lived connections or unpredictable traffic patterns, where even distribution is not ideal. Session persistence, also known as sticky sessions, is a load balancing feature that ensures requests from the same user are consistently directed to the same server. This is particularly important for applications where login information or session state must remain intact, such as in webmail services or shopping carts. The load balancer identifies the session and remembers which server is handling it, maintaining that relationship for the duration of the session. While it limits distribution flexibility, Persistence is critical for user experience in certain applications and often appears on the exam. Health checks and continuous monitoring are essential responsibilities of load balancers. They regularly probe back-end servers to verify that they are online, responsive, and capable of handling requests. If a server fails or becomes unreachable, the load balancer removes it from rotation, preventing traffic from being directed to a non-functional endpoint. These checks are automated and occur frequently, ensuring minimal disruption. This process helps guarantee service continuity, and you'll likely see exam questions related to health checks in high-availability environments. Another major function of modern load balancers is secure sockets layer offloading. Handling encryption and decryption requires processing power, which can burden back-end servers. By offloading these tasks to the load balancer, servers can focus on delivering application content. The load balancer handles the initial handshake, decrypts the data, and forwards unencrypted traffic internally. It also centralizes certificate management, simplifying security administration. For the exam, understanding how offloading reduces back-end load and improves performance will help you answer questions about optimizing secure communications. Load balancers are commonly deployed in high-availability configurations to ensure continued operation, even if the primary balancer fails. This setup typically involves redundant load balancer pairs, configured in active-passive or active-sective modes. In an active-passive design, one load balancer handles all traffic, while the other remains in standby mode, ready to take over if needed. In active activity configurations, both devices share traffic, providing higher throughput and automatic failover. Understanding the principles of high availability will help you recognize how critical services remain online in the face of failure. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Application layer awareness allows load balancers to make highly intelligent routing decisions. Instead of simply using transport layer data like IP addresses or port numbers, Layer 7 load balancers can inspect the full content of an HTTP request. This means they can look at uniform resource locators, check cookie values, or read headers to decide where traffic should go. For example, different URLs might be routed to different servers based on content type or service requested. This deep packet inspection enables load balancers to provide tailored experiences and route specific services to specialized backend servers. To external clients, a load balancer often presents a single IP address known as a virtual IP. This address is used by clients to initiate connections, even though the actual destination might be one of several backend servers. The load balancer uses network address translation, or NAT, to translate this public-facing address into the internal address of the selected server. This abstraction shields the internal network structure and simplifies client access. Clients do not know how many servers are behind the load balancer or which one they are communicating with, only that the service remains available and responsive. Global Server Load Balancing, or GSLB, takes load distribution beyond a single data center. It allows organizations to spread traffic across geographically dispersed locations using domain name system-based mechanisms. When a client makes a request, GSLB responds with the IP address of the data center best suited to handle it. This can be based on geographic proximity, server health, or response time. GSLB enhances global user experience by reducing latency and providing redundancy across wide areas. It's especially useful for multinational companies or cloud-hosted services with users around the world. The core goal of load balancing is to enable scalability. As user demand increases, more servers can be added to the backend without disrupting service. The load balancer integrates new nodes into its distribution logic seamlessly. This modular approach means that services can grow incrementally and adjust based on seasonal traffic patterns or business growth. On the exam, you may encounter questions about scaling infrastructure. Understanding that load balancers facilitate this process by spreading load across multiple servers is key to selecting the correct answers. Modern load balancers also incorporate several security functions. While they are not full-fledged firewalls, they can perform basic filtering to block certain types of traffic. They can also help defend against distributed denial of service attacks by absorbing or redirecting high-volume traffic before it reaches back-end systems. Additionally, load balancers hide the internal IP addresses of servers from external users. This provides a layer of protection by limiting exposure of the internal network structure, making it harder for attackers to target individual systems directly. Another important capability of load balancers is logging and analytics. These devices collect detailed data about session activity, including connection counts, error rates, and throughput metrics. This information can be used by administrators to understand usage patterns, detect anomalies, and troubleshoot performance issues. For example, if one server consistently has slower response times, that trend would be visible in the logs. Analytics from the load balancer provide insights into system health and help guide resource planning and scaling decisions. Integration with application architectures is a common use case for load balancers in modern environments. They are often deployed alongside microservices, where each service can scale independently. Load balancers also interface with traditional web stacks and cloud-hosted applications, managing user traffic across multiple containers or virtual machines. This flexibility allows load balancers to operate in hybrid environments, where workloads span on-premises systems and public cloud platforms. For the exam, it's important to know that load balancers are adaptable and support many application models. Summing up the advantages of load balancers, they are essential tools for improving the efficiency, availability, and scalability of network services. They manage traffic distribution, reduce the load on individual servers, and provide redundancy to keep services online. With session tracking, security features, and centralized management, they contribute to both performance and resilience. For any network design focused on high availability and scalability, the inclusion of a load balancer is not optional, it's a requirement. The certification expects you to understand these advantages and how they are implemented. To conclude, load balancers are central to modern traffic management strategies. They support intelligent distribution methods, perform health checks, offer secure front-end access, and allow systems to grow with demand. Whether positioned at the edge of the network or deep within an internal architecture, their function is always the same, ensuring traffic is handled efficiently and services remain accessible. Understanding their behavior, types, and integration points is vital for passing the exam and for building a foundation in enterprise network design. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.